Welcome guys. So the happiest thing for me is to make these kind of videos, and yeah. So hope you guys like it. So today let's keep doing our Lebesgue major theory. Yeah. So previously I said that I will prove these four of them because these four are very common in using the analysis, and basically are very important, especially for this the back monotone and the fructose and the back dominant. Right, but today let's prove the simplest one. Said that E F D mu is let's record E F D mu E. Okay, so this is very. I mean, if you use the back. Okay, so this one, right? Let's say the first one. It's very simple in the Riemann integral or Riemann something S, which I don't forget. I forget how to pronounce it. Integral, right? So this is very simple. You can prove by definition. You can prove by almost definition, right? Because you can prove the upper bound, the lower bound, and take the you can prove the upper sum and the lower sum, and then take the infinite soup. So basically, since in the Riemann integral, the integral, right, integral, let's say from A to B in one dimension has very clear explanation. You can just partition. So now this guy become almost trivial in this, right? But in the back measure, this is also this is not so trivial. So we need to give some results. I'll give some preliminary. So why is non-trivial? Because in the Riemann integral, we just do the interval, right? So otherwise, just the union of some intervals. But in the back measure, we are doing E, which is E can be some some subset of topological space. So E can be anything, which is measurable, not need to be an interval. And we also lose the concise explanation like the partition in the Riemann integral. So that's why to prove it, we need to something more. Okay. So theorem. Let's say f is measurable. Okay, so previously I used this notation, right? Probably this is not very good. So when I say f is measurable, I mean by definition, so it's x, f of x greater than a is measurable for every a, and the non-negative, let's say on x, and then let's say a is so this means that a is the back measurable. Okay, so now we're working on the back measure, and so a is the back measurable. So let's define phi of a to be f d mu a. Right, so since a is the back measure, okay, I mean, so a is the back measurable or mu measurable corresponding to this mu, this phi of a is well defined. Okay, by previously. So that phi is a countable additive on all the measurable set. So basically, I mean, you can view this function is a function on set, right? So just take f as another measure. So given a, you can try to compute the integral. Okay, and the second is that I mean, yeah, second just say so if you require f, work in f mu on x. So basically, let me just so this f on f mu means that sorry, f belongs to this integral of by mu means that if you write f in terms of plus and minus, then how should I say? Okay, so this L mu since it's non-negative, right? So I just require that I just require that at least f d mu a is finite. I mean B, so 2 is a special case of 1. Okay, and also for plus and minus. So for any non-negative, for this L mu means that if you write f equals to f plus minus f minus, then means that these two are integrable and they are both finite. So 2 comes from 1 if since f plus and f minus are non-negative. Okay, so proof A. Let's say so we want to show this. We want to show this phi has this property. Let's say n to infinity. I use n. Okay, and if let's say each an which is measurable, and also there are pairwise disjointed. Yeah, so definitely for I not the same as J. Okay, so the idea is that so let me just usually to prove something in the major theory, usually we start from some simple function, right? So and then we know that any measurable function for non-negative measurable function, you can find a monotone simple function which approach to it. So this is the property, the key step that usually you can prove in the analysis. Okay, so step one. So step one is using a simple function. I mean, or characteristic function. So characteristic function. Okay, so let's say we use f is let's say suppose f is characteristic function, then the property, right? If the f is characteristic function, that means what? That means this f, let's say f is something characteristic function on some set ke, right? By definition is kd mu on something, let's say a, you just mu of a intersection with e, and the mu is already what? Mu is already countably additive. Okay, so proof done. Okay, so step two, if f simple. Okay, so remember the simple function is a linear combination of a characteristic function. So the countable additive works for a characteristic function, then it should work for a simple function. So done. Okay, so the general case. So the general case, which is a step three. Step three using the definition, right? So let's just quickly remind that what is the definition for a non-negative function? Basically, it's defined to be all the, let's say, soup of this s d mu, where act on e, and the s is all the simple function which is less or equal to f. Okay, so let's say I take some simple function which is positive, and let's say s d mu is equal to n from 1. So s is a simple function, right? So definitely it has the countably additive property. So let's say n will less than equal to, right? By definition, this is phi an. Okay, right? Because this definition, this guy is this guy, right? This guy is greater or equal to this guy. By definition, is phi an defined to be the integral of f on an, which is integrable. So you use this as a soup, right? So each soup for each n, this soup greater than itself, greater than this any simple function, right? This is the for each simple function satisfy this property. Okay, so analysis. So if you take soup, right? You take soup, right? So soup, the left hand side tell you that the phi of a less or equal to this. Okay, so we need to find another direction. So this is the first directions, and then we hope to find another one. Okay, so let's make some remark. Oh, so remark is that if phi of a is infinity, then it's no need to no need to prove, right? I mean, otherwise, because phi of a is infinity, then this guy must be infinity. So it's make no sense to talking about to infinity, which one is larger, right? So one can say, and also if phi of a is infinity, then by definition, you know that phi of a is greater than phi of an. Okay, the reason is that a is a union of an, right? So that means phi of a is greater or equal to a phi of an, right? By the property that we just proved that 6 is non-negative and your integral in your integration range is larger. So if this guy, so if this guy is infinity, and that one of these guy must be infinity. So it did not make any. It's not important to talking about this case. So I can further assume this 5a is less than infinity. So that means for each n, 5an should less than infinity. Okay. Otherwise, if there's any n which 5n is non-infinity, then 5a greater than 5n, then every guy become infinity. Okay. So this is the suitable assumption. Okay, so now we need to do the old stuff. Let's say given epsilon greater than 0, and by soup we can there's a simple function s such that let's write it simple such that 0 that's equal to s, that's equal to f, and such that what such that say a1 s d mu greater than equal to a1 f d mu minus epsilon. Right, this is a property of soup. The a2 integral of a2 integral of a2 such that s d mu greater or equal to a2 f d mu minus epsilon. Okay, so if you combine these two, right, you get phi of a1 union a2, which is greater or equal to a1 union a2 s d mu. Right, this is the property of phi, and which is equals to, right, so s is a countably additive, so you can write this as a1 union a2 f, combine these two to epsilon, and epsilon can be arbitrary, right? So basically you prove that the phi of a1 union a2 greater or equal to phi of a1 plus phi of a2. Okay, right? So if you take, okay, so we're very happy that if you, so for each n, right, so you have a1 union a2 union an greater or equal to summation of phi ai I from 1 to n. Okay, and then you know what? You know that a is greater than, of course, a is covers all the, let's say a k from 1 to n. Right, so this is phi of a. So if you take, and this is for every n, right? So if you take n to be infinity, then you prove that the phi of a greater than phi of a and n from 1 to infinity. So this is another directions, right? So compared to these directions and these directions, which we prove countably additive. Okay. Okay, so let me just give you a remark and also introduce a very important idea about measure zero. Right, so I mean, the probability theory or other the back theory or whatever, and you sometimes need measure zero. So measure zero means that there is a set, right? So which is zero. You measure zero. Okay, but sometimes there's a notation that one can define a f, which two functions is equivalent on E if let's say x, which f of x is not the same as g of x, intersection E is measure zero. So basically, or you can just say that there's no volume for their difference, right? So they maybe at most countably difference, then or they have some Cantor set difference, but they have their volume zero. Okay, so obviously that there is a immediately results that is non-trivial. Basically say that if f and g are E, if their difference are measure zero, then the f and g integral are the same. Okay, and the reason is that you can write, let's say E is let's say E1 union E2, and such that E2 is their difference, right? So let's say this guy is E2, and they are disjointed, right? So E1 is f equals to g, E2 is f not the same as g. Sorry, so this, yeah, so E1 is set x, f of x equals to g of x, and the E2 is there into E2 is there difference, right? So which tell you that f d mu E is the same as f E1 d mu plus E2 f d mu, and the g d mu E is the same as g d mu E1 plus g d mu E2, right? And since they are measure zero, so these two are zero, as I just proved before. I think previously I proved that if your integral on some measure zero set, then you will be in zero, right? So they are the same. Okay, so most of the theory in the analysis are always true if you add this measure zero consideration, right? Because if you add something which is non-measure zero, then the back measure cannot detect it. Okay. Okay, so everything I said can be done, can be added, addressed when the measure is zero. This is the usual argument. Okay, so basically, let me just write down. So if a property, let's say a property P holds, let's say holds for every x belongs to E mod A, sorry, delete A. So A is a major zero part. And if mu of A 0, then usually we will say that P holds almost all for x belongs to E. So basically, what I'm just saying that so usually people say P holds almost all for x belongs to E, means that the points which do not have this property has measure 0. Or basically, people like to say almost everywhere. Okay, so one example let me just mention. So in the analysis, I mean the undergraduate analysis, there's a theorem that says if f belongs to AB, and which is, let's say the first kind, suppose f is continuous, let's say f is continuous on AB, and then non-negative, let's say, then if you know the integral of AB to is 0, then you can prove that f is 0. Okay, by using the epsilon delta argument. And so you can, if you do not assume that f is continuous, you just assume that f is non-negative and measurable, as f is measurable or bounded, and you can prove that you can still define this, right, by via the Lebesgue measure. Suppose the Lebesgue measure is 0, then then people will say that f equals 0 almost everywhere. So use AE. Okay, so the proof is the same as you proved previously, but since this Lebesgue integral cannot detect something which is measure 0, so you can easily. So this is why people sometimes like to say something 0 almost everywhere, because the point which do not satisfy its property has measure 0. Oh, type. Okay, theorem. Somehow some things. Sometimes I feel very pathetic if I'm just doing this stupid video and fulfill my dream. Okay, so if f belongs to measurable, basically in this case, which is f plus finite and f minus finite, then one would able to prove that the f absolute value become measurable, or basically integrable. Okay, and let's say on E is less or equal to f d mu on E. Okay, let's give it a proof. Yeah, this is after this proof. We will finish this video. In the next video, I will talk about the monotone Voxels dominant convergence, most important three theory in the major theory. Make a video to fulfill it. Okay, so let's write E equals to A union B, where A is a set where f of x which will equal to 0, B is a set x such that f of x less than 0. So there are disjoint union, right? Trivial. And then by definition, A, B are measurable because f is measurable, right? So previous definition that A, B are measurable since f is measurable. So this is a property. So I can write, let's say I can write this f absolute value d mu E in terms of, let's say, f d mu A, f d mu B. Okay, right? And if I write f equals f plus minus f minus, when in the A part that this is positive, right? So this only take the positive part. And for this, I only take the negative part. And by the definition, which f is integrable, means that the positive parts on E, the positive parts on E is less than infinity. And the positive part is less or greater or equal to if you take this A, right? Because A is a subset of E. So this guy will less than infinity, and also this guy will less than infinity, so total will less than infinity. Okay, so we prove that these guys satisfy this property. And works on this. And wait, sorry, I didn't prove this, I only proved this. Okay, so yeah, so previously I already proved that f is a integrable. I mean, not infinite, not finite, but the integrable by a property of sigma ring. But in this case, we prove that f is integrable on E. So basically, we prove that their value is finite. Okay, so it's a little bit different from the previous one. So previous one, I only proved that f is integrable, but not finite case, maybe infinite, but we prove that f is a measurable function, and f the absolute value will be a measurable function. Okay, so finally, we need to prove this guy, right? We need to prove this guy. Okay, so notice that. So f is less or equal to f as the absolute value and greater or equal to negative absolute value, right? So by the property of the integral, and you can easily say that this f d mu e is less or equal to f absolute value d mu e, right? By the previous results, that if s less or equal to g, and I say that you can easily prove this. So this is the previously I already proved this. Okay, and this is trivial. I mean, if you want to prove it, it's very trivial. Just prove that every non-negative function integral should be non-negative by definition. This is just okay. And then okay, you can see that negative f d mu e is equal to f absolute value d mu e. So combine these two. Nice, simple proof. Okay, so yeah, so we prove this absolute value version, which is a simple example. And the next video, I will prove the Lebesgue dominant fractal statement and the Lebesgue Martel fractal statement, Lebesgue dominant convergence, which is these three are most important technique in the, I think at least the first part of real analysis. And I will finish the routines analysis discussion in 3 or 5 videos. And after that, maybe a few months ago, and we'll talk about the sigma approach and the differentiation, and also how to construct a non-measurable set. Bye-bye.